So it's a pleasure to introduce the last speaker of today, Victor Ginzburg from Santa Cruz. And he's going to talk about filtered symplectic homology of prequantization bundles.
Thank you. I'd like to thank the organizers. It's always a pleasure. Well, I'm afraid I'm not alone here and I'm saying something trivial, but it's always a pleasure to visit this beautiful city. I enjoy it enormously each time I come here, and the weather is beautiful and the beach and everything. So I'll try to limit my talk to 1 hour. We have other things to do. And this is a joint, very much work in progress with my student Jiangmin Sean. And kind of, I'm afraid what I'm going to say is, what I'm going to talk about is not a general interest talk. In fact, it's a fairly elementary discussion of a rather technical object, but so be it. Every once in a while it happens. So I'm going to start with the motivation for the questions, for studying this symplectic homology of prequantization bundles for me. And it comes from actually our joint work, or my joint work with Başak Gurel and Leonardo Macarini. So throughout this talk, GGM will stand for Gurel and Macarini and myself. Let's consider the following situation. We have a circle bundle over symplectic manifold. This is a prequantization bundle. So B sigma is symplectic. This is a circle bundle. And the first Chern class of this circle bundle, this is projection pi, is equal, depending on your conventions, it should be probably something like -1 over pi, and then the cohomology class of sigma. There are different conventions here. So I'm going to take a connection form alpha. This is a contact form. Its Reb orbits are very simple. These are simply the fibers of this fibration, possibly iterated many times. So there is nothing interesting here so far. But if I take some other contact form, giving rise to the same contact structure, this becomes a dynamically interesting question. And the main sort of the main question we wanted to study here is how many simple periodic orbits the Reb flow of alpha has. So let's denote the number of, or the set of simple periodic orbits, something like P with this weird dot on top of it. So the question is how many simple closed orbits this alpha has. I'm going to give 2 representative theorems here. Theorem 1, GGM. And I will be rather sketchy, like stating the conditions of the theorem. So I'm going to start by starting with the assumptions. M admits a symplectic filling, or symplectically spherical filling, W, such that the pi1 of M injects into pi1 of W. Then there are some further technical conditions. For instance, the minimal Chern of the base is not too small, and the odd homology of the base is 0, and maybe a bit more. And then there are some index conditions, or maybe I should say it differently. Then alpha is non-degenerate, and then there are some index conditions. And under this assumption, we have shown that the number of simple closed-trap orbits of alpha is bounded from below by the sum of the Betti numbers of the base. This is actually a very reasonable result. Let's look at the collections of sort of this. This is reasonable to expect. Let's look just at the case when alpha is equal to alpha naught. So what happens? Simple orbits are simply the fibers, uniterated fibers of this projection. When I perturb this, the M, it's going to, I mean, the fibers are going to split into how many orbits? What's the minimal number of orbits we would expect? Well, the minimal number of orbits is governed by the equivariant Morse theory of M, which is the same as the Morse theory of B. And with all these assumptions, this is what we expect to get. And then it's reasonable to think that if the perturbation is not very small, you still have the same result. And actually, add to that, this result is sharp, at least in many examples. Now, the second theorem, I'm going to sort of comment on them both a little bit later, but I want to have them side by side. Theorem, that was our theorem 1. Theorem 2, we refer to it as the contact-Conley conjecture. And this is, again, GGM. So now the assumptions are a bit simpler. First of all, I want to assume that sigma, the symplectic form on the base, is aspherical. And I want to assume that pi1 of M of the fiber bundle is torsion-free. And then there is a little technical assumption. I need the, so if I denote the contact structure here, the connection itself by Xi, this is a complex vector bundle. I want to assume that C1 of Xi is atoroidal. Its integral vanishes over all tori. Then there are actually infinitely many simple periodic orbits. This is a contact analog of the Hamiltonian Conley conjecture. So a little remark here is that these conditions are automatically satisfied when the base is aspherical. In the standard topological sense, all higher homotopy groups are 0. For instance, these conditions are satisfied for surfaces. this theorem is particularly dear to my heart because it has a very nice consequence. So I'll just mention it very briefly. Let's take the following situation. Let's be sort of application to magnetic fields. Let's consider the following situation. Let B be a surface of genus greater than or equal to 2. Sigma be a non-vanishing 2 form on B. Let's take the cotangent bundle over B with a twisted symplectic form, which is simply the standard one plus the pullback of sigma. And finally, let's equip B with the Riemannian metric and take the kinetic energy Hamiltonian squared. Then the Hamiltonian flow of K with respect to this twisted symplectic form describes or governs the motion of a unit charge on the surface, with sigma being the magnetic field. So with very little effort, one can derive a corollary from theorem 2 that every level, every low energy level carries infinitely many simple periodic orbits. So for every sufficiently low energy, there are infinitely many simple periodic orbits of a charge. Now, simple means not iterated. So simple, let's look at an orbit. Okay, simple, I should emphasize the difference with differential geometry. In differential geometry, simple means without self-intersections. Here, in this context, simple, well, let's take a periodic orbit. You take a point, go down the flow, after some time you come back. So far this orbit is simple. If you continue going down the same orbit, it becomes iterated. In differential geometry, they say prime or iterated. Okay, so going back to these two theorems, well, here obviously there are tons of examples. With theorem 1, the situation is a little bit more subtle. What are the examples here? Of course, when we are in this situation, one may try to take alpha and fill it in by the disk bundle bounded by M. And I'm going to show how to do it, but unfortunately, this filling will never satisfy the first condition of the theorem. Namely, pi1 of M into pi1 of W will never be an inclusion. The free homotopy class of the fiber is killed. And this is kind of the most important of the free homotopy classes for us. So W is never the disk bundle here. So the most interesting and admittedly the most important class of examples here is the cross spaces. For instance, it can happen that M is the unit cotangent bundle to some other manifold X, and then I can take the filling not by the disk bundle here, but by the ball bundle there. And this is the filling we would work with. This is the case, for instance, when X is the n-dimensional sphere or m-dimensional sphere, then B is the oriented Grassmannian G2 m plus 1. And I can study the closed geodesics on the sphere as closed Reb orbits on this principal circle bundle. So this is one situation where this theorem works pretty well. However, still, I find somehow this way of thinking totally unsatisfactory, because kind of here I have my circle bundle. It comes with a very natural filling by the disks, and it's nowhere used. In the proof of the theorem, the disk bundle. So the proof of the second theorem genuinely uses the contact homology. And the reason it needs contact homology is that the contact homology is graded by free homotopy classes. So that's kind of the only reason. This is a consequence of the fact that the contact homology graded by the free homotopy classes. And it's absolutely essential to distinguish fiber from the second iteration of fiber, from the third iteration fiber, etc. This, in the proof of this theorem, like the iterations of the fiber replace the iterations of a Hamiltonian diffeomorphisms in the Hamiltonian Conley conjecture. Once I start using symplectic homology, with respect to the disk filling, all the fiber becomes contractible, all iterated fibers become contractible, and all of a sudden they're sort of all combined together. Now, so with this motivation, so I thought, what's going to happen if we just look at this, look at the filling by the disk bundle, and see what we can say about it? I'm going to focus on one specific case when the manifold B is symplectically spherical. That means that the first Chern class of B on pi 2 is 0, and sigma on pi 2 is 0. This kind of rules out any applications to this theorem, because in this theorem I cannot afford having B aspherical. But we will see at the end of the talk that one can reprove theorem 2 by this method. Or by the method I'm going to discuss, or using the machinery I'm going to discuss. So now let me actually describe the setting. instead of looking at the circle bundle, I'm going to look at the line bundle. I'm going to denote this by the projection. And I'm going to think of the connection form alpha naught as extended to E as a homogeneous form of degree 0. Then E carries a symplectic form, which, like, there are different ways to do it. The pretty much all equivalent to each other. Maybe the convention I want to use is this. So this is the omega, which is the pullback of sigma to E, plus the, well, what I'm trying to do here, I'm just looking at the polar coordinates on every fiber, extend these polar coordinates using the connection form, and write down the area form on the fiber. So this is the symplectic form. In algebraic geometry, E would be called like the negative line bundle. This form is not entirely exact, but it's very close to being exact. And I can write it as d of 1/2 1 plus r squared alpha naught on E minus b. All right, and for the time being, let me look at the unit disk bundle, or a disk bundle with some radius r. Does not matter which one I take. And maybe one more thing I want to keep in mind. If sigma is aspherical, the long exact sequence for the fundamental groups of this fibration splits, and we have something like 1 pi 1 of the fiber, 2 pi 1 of M, 2 pi 1 of B, 2, 1. It's essential here that sigma vanishes on pi 2. So here I have my Z. This is the group. Well, this is the projection, and the kernel of that projection is exactly Z. It's generated by the fiber. The choice of alpha naught, the choice of connection, or if you wish, the fact that M is actually a principal circle bundle, give me a generator here. So I know, I can tell +1 from -1 now. So I'm going to have it fixed. So I'm going to, so what I have here is the fiber traversed in the opposite direction, iterated fiber, etc., etc. All right. The first theorem I want to quote, the first thing that sort of is relevant here is the vanishing theorem. Ancha. I probably should add here Ritter and Chilibach Frauenfelder. And what it says is that the symplectic homology of W is equal to 0. Basically, when the homology is equal to 0, in this context, it tells you that nothing interesting happens. It's essential, so the only, and I'm going to reprove this theorem in 5 minutes or so. It suffices to assume, so what you need is that sigma on pi 2 vanishes. Actually, you need either one of these two conditions. You don't need both of them simultaneously. What's interesting is, and this is an observation by Ritter, is that it's not true in general. And now, so that's the first fact I'm going to keep in mind. Let's call this the vanishing theorem. And now a totally non-trivial fact. And this is Bourgeois and Orange a while back. So when you do symplectic homology, there is such an object as C symplectic S F minus of W. So let me recall very briefly the definition. What do you do when you construct symplectic homology? You take your filling, you add to it the cylinder 1 through infinity cross W, cross the boundary of W. You take the Hamiltonian which is nearly 0 but slightly negative on W, then it's convex, and then it grows linearly with R. You do the Floer theory for this Hamiltonian, and then let the slope here go to infinity and pass to the limit. So this part as symplectic homology, symplectic homology minus. So when you do Floer theory for this Hamiltonian, what you need to do, you need to actually perturb it slightly to make it non-degenerate. As you do so, you are creating some trivial orbits here. This part comes from trivial orbits of the perturbed Hamiltonian H. Now, when the filling is Liouville, all right, maybe actually here is something that I should, maybe I should say, like trying to work in this setting, two things are different from, say, the most standard versions. One is that the symplectic action is different from contact action. And I'm going to elaborate on this a little bit later. And the second is that pi 1, as we already hear, pi 1 of M to pi 1 of W, pi 1 of W is here, is not 1-to-1. So because the symplectic action is different from the contact action, usually you show that this homology is well defined, or that constant orbits of the perturbed Hamiltonian form a subcomplex by just arguing that it's the same as looking at the orbits with action smaller than some delta. Indeed, all these orbits have zero action. These orbits have some positive action. And because the Floer differential decreases the action, these guys form a subcomplex. So this is true in the Liouville case. In this case, you only have inclusion. OK, in this case, what can happen is, because of the way you evaluate the action, a non-trivial orbit happening somewhere here may have actually negative action. Nothing precludes this, even though I don't know on the spot examples where it happens. So what Bourgeois and Toancha show is that there cannot be, so if there is a non-trivial orbit here, there cannot be a Floer trajectory from a trivial one to a non-trivial one for purely like different reasons. This is actually an absolutely non-obvious statement. So I find it kind of, unfortunately, there is not like a very localized reference to it, but this is what they sort of do. The SH minus into is well defined. And from there, we can actually easily see that there is an inclusion that of the negative symplectic homology to the filtered part here, but possibly not an equality. And the corollary of this fact is that I know what the interesting part is. So once I have a subcomplex generated by these constant orbits, I also have the quotient complex, which is in effect generated by non-trivial orbits here. And the corresponding homology is called SH plus. So I have now the long exact sequence SH minus to SH all to SH plus and continuing. So star, 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 SH minus, star minus 1. Every SH term is 0 by the previous theorem, and so I know what the plus part is. This is the same as the minus part up to a shift of degrees by, so this map is an isomorphism by 1, and this part is very easy to calculate. This is the same as the homology of the base. And I have to, up to some shift of degree, so it's negative n plus 1, I think. So now I know the interesting part of the homology. All right, but so far it was all about the round disk bundle. If I'm interested in dynamics, this doesn't tell me anything new because I know what closed rep orbits are there. There is nothing more trivial than that. So let's go back to what we want to study. We want to study the Reb orbits of some form alpha, which is f. F is non-negative. Sorry, non-negative times alpha naught. Raising the vanishing theorem. So, and staring at this formula, I observe that if f so I want to, there was an important formula here about the prequantization line bundle, which is just rephrasing this, which says that the pullback of the alpha naught is, no, sorry, the pullback of sigma is the alpha naught. So this is where the second formula comes from, and I think let's do it this way. I think it's better now. So I observe that just by, once I have a function f, setting f, or setting r to be determined by the condition 1 plus r squared is equal to f, which of course requires f to be greater than 1. I can realize M as a fiber-wise star-shaped hypersurface. So this would be our round disk bundle. The blackboard is a fiber. And the M now is given just as a level of R determined by this condition. And this is the boundary of the star-shaped filling. Well, we still, well, the vanishing theorem still applies. The symplectic homology is still 0. In fact, if you wish, the symplectic homology of WF is the same as the symplectic homology of W1. So it's 0, and everything I said before carries over for this global symplectic homology. The assumption that f greater than 1 is not really restrictive. When f is greater than 0, I can multiply it by some factor just to ensure that this will change all periods simultaneously, and I can make sure that f is greater than 1. So now let's examine very quickly the difference of actions. As I said here, sort of the contact action and the and Hamiltonian action are different. So once I know this, all this exact sequence stuff, SH plus minus, carries over. So, but the difference of actions is interesting. So let X be a map from S1 to our contact manifolds. And I want it to be in the free homotopic class of the iterated fiber. Somewhere here. This is our Z. So let's just give it a name, call it K. There are two ways I can evaluate the action. There is a contact action, which is simply the integral of alpha over x. And there is a Hamiltonian action, I omega of x. So remember, the Hamiltonian action is obtained by integrating the omega over a disk bounded by x and subtracting the integral of the Hamiltonian. As I do my limiting procedures, the orbits will occur lower and lower in this picture, so this part will go to 0. And so what I need to do to evaluate the Hamiltonian action, I need to take a disk bounded by x. X is contractible in W, so such a disk exists, and evaluate omega. Now, unfortunately, this disk intersects the 0 section, and Stokes' theorem does not apply. Alpha is alpha, which I can take like this guy. It's a primitive of omega away from the 0 section. And the two things are not equal. In fact, the difference between them is completely determined by the free homotopy class of x. This actually it's a totally elementary fact, but somehow I still find it counterintuitive. And in some sense, this is the Tom class of E evaluated on x. Explicitly, it's something like negative pi over 2 times k. That's kind of an elementary exercise, but this formula, well, this is always a positive term. This can be positive or negative, but this formula actually shows that there is absolutely no reason to expect this number to be positive, although somehow it happens to be positive in the examples you can put your hands on. So that's kind of the explanation to the fact that the contact action is not equal to the symplectic action, and the filtration in the symplectic homology is by the symplectic action, not by the contact action. And this is what accounts for the fact that, in general, you have the inclusion, but possibly not the identity. Some of these positive guys can go into the negative domain. Theorem. Theorem, let's put it here. The domain W is stably displaceable. That simply means that if I take W and crosses as it will, of course, it's not displaceable because the 0 section is not displaceable because the cohomology class of sigma is non-zero. There is no way, no chance to move it away from itself. So this is, instead I'm going to do a no trick that goes back, I guess, to Schlenk and Polterovich, whichever way you look at it. I'm going to take WF and product it with S1 and think of it as a subset in E cross the unit cross-decotangent bundle to the sphere. So now, at least topologically, you can displace it, and I'm saying it's displaceable regardless of what f is. You can move it away from itself by a Hamiltonian diffeomorphism. Unfortunately, I don't know a simple, transparent proof of this theorem, although I'm kind of, at the moment, I believe it is correct. I'm going to prove a version which is actually sufficient for our purposes, which assumes that f is close to 1. So that, in fact, my f is very near here. So to this, so I'm proving a very particular case. This is simply saying that B is stably displaceable. Or in other words, B cross S1 is displaceable in this product. Well, look at B cross S1 in this product. So here is B, here is S1. This is a totally non-coisotropic submanifold. And then, in addition to this, that the symplectic orthogonal to it has a non-vanishing section. This non-vanishing section is simply vector field tangent to S1. And then there is a theorem of Gorel that says that a totally non-coisotropic submanifold satisfying these two conditions is displaceable. Which proves this case. The general case, you need to really sort of look into how things work. So the consequence, of course, is the vanishing theorem. Once things are displaceable, the homology vanishes. Kind of by now, it's a standard argument. So one corollary here is indeed, by now it's a pretty standard argument that the symplectic homology of WF times a small annulus here is 0. And applying the unit formula, we will see that the symplectic homology of this part is 0. So this is pretty standard. But in fact, one can do better. And that's something which is much less known. One can do this. So instead of looking at the global homology, let's fix some action interval. Then I can do the same length interval, but shift it to the right. There is a quotient inclusion map. This interval may be very long with respect to the size of the shift. But nonetheless, let's consider this map. I claim that this map is 0, and now I have to put a quantifier here. There exists C such that for any interval I, no matter how long, this quotient inclusion map is 0. In particular, if I take the interval from negative infinity to infinity, this map this is negative infinity to infinity. This is negative infinity to infinity. This is the identity map. And therefore, the homology is 0. So this is the sort of the reference here, how to get it from displaceability is, there is a paper by Sugimoto, who proves it in, well, we have known it for a very long time, but the existing reference is Sugimoto in the Liouville case. It's not difficult to prove it. It's not difficult to prove it in the symplectically spherical case. In fact, unfortunately, these two statements are equivalent. So in one direction, I've shown you the proof. In the other direction, there is a, so in this direction, you take I to be negative infinity, infinity. And in the other direction, K Erie showed me a very simple, purely algebraic argument that sort of shows that if this is true, then the same is true. You get slightly different constants. In this case, you get C to be the displacement energy, and in the opposite direction, you get C to be the first symplectic capacity, or the first spectral invariant. I'm not going to define it because I'm running out of time. So in any event, I think this way of looking at the displaceability, the effect displaceability, is probably not well known. Now, what about symplectic capacities? Well, once we have symplectic homology, we also have equivariant symplectic homology. And equivariant symplectic homology, at least the interesting part, is simply generated by closed Reb orbits. This is the homology of some complex, literally generated by the closed Reb orbits. I think Bashak and I, in one of the papers, describe it in detail. So there are all the kind of attributes here. You can put plus or minus or nothing. S1 stands for the equivariant, and then you can fix also the action interval. So here is a simple fact that if the ordinary homology is 0, then the equivariant homology without any attributes is also 0. This is, I don't know, Seidel, Bourgeois, Ancha, Hutchings, I suppose. But here is a peculiar observation. This fact, in contrast with what we believe thinking in terms of Morse theory, does not seem to have an equivariant, does not seem to have a filtered analog. So if I put I here and I there, then this is probably wrong. I put it this way. The constructions I am aware, all constructions I am aware, including my own, do not go through in the filtered case, and I have kind of reasons to believe this wouldn't be true, and maybe the remark is simply if it were true, then this fact would have an equivariant analog, but it does not. Well, in any event, it's probably not true in the filtered version. All right, so using all these long exact sequences, I can easily understand what the equivalent homology is here. SH plus S1 global simply looks like the homology of the base times the homology of the classifying space. And here I think I have the same shift, negative n plus 1. It's convenient to think of this guy as a polynomial field in some extra variable h, and therefore here on the right I have a sequence of elements uk, which looks like the fundamental class tensor h to the k. There is a Gaussian long exact sequence with the connecting operator d of degree -2. This is what then, this is kind of the symplectic homological version of the U operator then spoke about. And it was introduced by Bourgeois sort of years back in this context. And so du descends uk to uk minus 1. And here is an easy consequence of the everything else I said, is that, well, I can associate spectral invariants or capacities to these classes. So let's call them CKS1. Then, first of all, this is a strongly increasing sequence. Sorry, it is an increasing sequence. It is strongly increasing sequence if, so this is again Sean and myself, if all simple orbits are isolated. And secondly, the gap between consequent capacities is bounded by whatever we have here in this sequence. Now, all of this actually works for the sphere and gets, of course, much simpler. So this result, it would probably be marginally new for the sphere, which does not quite fit into this picture. So it's tempting already for the sphere. It's a well-known open question if the normalized if the sequence of normalized capacities converges or not. So unfortunately, kind of for a while, I thought that this would be an easy consequence of the bounded gap, but in fact, it's not. It does not imply that it converges. And now I have 2 minutes for probably maybe the most interesting part of the talk. And this is how do we recover the contact-Conley conjecture. Through this machinery. What is this extra structure in this case, it would be the extra structure in the plus equivalent symplectic homology that is sort of responsible for the free homotopy class in the fiber. The fiber is contractible, so there is no free homotopy class. It's always 0. How do you tell twice iterated fiber from 3 times iterated fiber? And so the answer to this is actually, in retrospect, it's very simple. What you can do, well, when you take your constant Hamiltonian, let's also take J, an almost complex structure such that the 0 section is an almost complex submanifold. Then the Floer equation becomes a Cauchy-Riemann equation near the 0 section. So solutions of the Floer equation are simply holomorphic curve. And that means that the intersection of U with the 0 section is always non-negative, which means that this is, I think, in elementary complex analysis, which I think you will teach soon. It's called the argument principle, something like that. So it means that the Floer homology, if I look at the part of the complex, I don't know, S, C, F, H, K, generated by non-trivial orbits in the free homotopy class of the fiber, iterated k times or fewer from negative infinity to k. This is actually a subcomplex. The Floer differential can only increase this number. After that, I have the related, I get the related filtration on the symplectic homology, equivalent symplectic homology. And after that, I can take the graded groups associated with this filtration, which I can now, this all is totally invariant. I can use any contact form to calculate it, so I can take alpha naught. And for alpha naught, I know everything, which tells me that these groups are exactly what they should be. This is I exactly recover my contact homology for the k-time iterated fiber. And after that, I can do the proof. Interestingly, this thing actually, in some form, generalizes to higher dimensions, to the problem of magnetic flows in higher dimensions, but it becomes a much more involved algebraic structure. It's not a filtration anymore. It's some action of the fundamental class of B on the homology. So this is kind of the idea of the proof. Let me stop here. I'm already over time.